Gents at the back, do come in. I'm only just starting. Right. So I'm Nick Bailey. I work for Introduzione. So when I originally proposed, put forward an abstract, I'd been looking at some work on the analytical side of curve fitting and that sort of thing. However, once you start looking at data, you usually find other interesting things. And so I'd like to talk to you about some other sources of variation when you do J1C measurement or determination. So I'll just talk, in overview, I'll talk just very briefly about unloading compliance tests, and then what sort of the fitting process that usually goes on, and then talk about some experimental issues that that I see when I've looked at a number of different data sets, and then show you a little bit of what happens when you use different machine control modes. So, unlike unloading compliance tests, hopefully most of the audience are fairly familiar with these, but just in summary then, we're constructing a resistance curve for J delta A, and we're periodically unloading the specimen and working out the compliance so we know how far we've plastically deformed it. In terms of determining our crack extension from compliance, and correct it at relevant points, and then we determine J1 critical from the intersection of the fitted curve. So, typical data set might look something a bit like this. So you've got ramping up, and you've got unloading points all the way along. This is just an example from a 316 stainless steel. What are we going to do with that data? Well, first we're going to put a linear fit for each unloading or reloading line. You have a choice which one you use, and obviously you have to. There is some variability in the selection of the linear portion of that line. We work out the compliance, the rotation correction, and we correct. Once we've got this, we correct for what the A naught is, or the apparent A naught. You're making a polynomial fit there, so your choice of equation of order is going to affect that. Also, at the very early sequences may not fit very well. And then we are incrementally determining J between the points that we've been ascertained. Trapezium rule, as you'll probably be familiar with from both ISO and ASTM standards. So there are various points there that you could maybe come up with some variation. And again, at the last point of fitting the J delta A curve, the recommendation is to do a linear fit to log plot. Now, so that works pretty well in a lot of cases. So you've got your excluded data down here, up there. You've got the solid blobs. I'm sorry, they've not come out very well there. In the middle here, where we're doing our linear fit, and in a lot of cases, it's not terrible. But things can go a bit wrong if it's not actually a very linear thing you're trying to fit. Similarly, if you've got a choice of using the unloading or the reloading part of that point, then you actually get a bit of an offset in compliance there. So, various things, and these are just fairly naturally occurring, as they were, within the data. And you get a typical that looks like that. For example, in the standard things that you should be familiar with if you do J1C tests. But then I started looking at data sets carefully and thought, well, hang on, there's something a bit funny here. We're supposed to be loading up and then reversing. And you find that in certain circumstances, there are certain setups, you get this, you stop loading and then you pause for a little while before you unload. Usually this would be only a fraction of a second, but when things go wrong or it's badly written software or badly configured, then you get a big pause, and what's happening here is you're actually relaxing the load, and mouth opening is increasing, despite the fact you're holding your machine still. So so that brings about a question, to me at least, of what are we analysing? So conventionally we use the load line displacement, the load line displacement we actually calculate from the crack opening displacement, sorry about that, and the force at the peak. So that is at that point there. But we always use the compliance at the unload or unload-reload point. But as I've just shown you, that's not always the same place. So if you compare the results, just taking that example that we saw, if you go for the theoretical point for the maximum load, you come out with one answer. You actually go down to the point at the end, just before you start unloading, and you get quite a different answer. So more than 5% difference in your result. Which I know we get variability here, but that's seems quite noticeable. And just for reference, from the same data set, you do get a distinct difference between using unloading and reloading data using standard fitting data. That's without too much fretting. So, is this a test system problem? It should be your question to me as someone who works on developing these. The answer is maybe, I'm afraid, like so often. So that you've got the control. Now, from the standards, we usually have a recommendation that you control the actuator position. So you're controlling the load points. If you're looking at a CT specimen, that's the separation of your two loading holes. And you do then have a question of how quickly should it reverse. There is some software where you deliberately introduce a pause between unloading. There's some where it is expecting it to be instantaneous. So how fast should you reverse the machine direction? And indeed, how quickly should it travel? Also, data acquisition. What you saw on what I showed you just now is a system where it's discarding the data between the end of loading and the beginning of unloading. Now that's something that you wouldn't want to do, and I was not happy with that data set, but I chose it as an example of what can go wrong. Also, when you define the end of reloading, what I didn't show you on that chart is that do you choose your maximum load as the true maximum or the way you start unloading from? All of these things are building up an uncertainty. So just to show you, show you that the machine is actually doing what it should do, you've told it that it's been told to control position. It is. It's there and it's staying absolutely where it was. I've got load up this axis, position across. It's staying exactly where it was. Meanwhile, that same segment over here on the cod gauge, it's extending away quite happily as it's relaxing. If we just analyse that, now you've got to excuse the fact that there's a discount continuity, but there is no data for me to work with here. You've got, here we go, we're unloading at this point. Sorry, I should explain. Blue line is the COD gauge. Green line is an estimation of the rate of change. So unloading here, nice and stable. Reloading, nice and linear, and nice and stable. And then we start to extend the crack again, and your cod gauge rate of change, it's accelerating away. So, well, good. Go on. Waiting for it to advance. Okay, so what I've just to show you on one specimen in the same point, I've set up a very strange test here where I've got 4 different control scenarios. So this is what we'd be hoping for, just as standard, that we more or less immediately reverse. So we're loading up, and we turn around and go straight back. And you can see there is a distinct offset between loading and unloading. Unloading and reloading. What happens if you've got a pause, deliberately or otherwise, is you get to this point and you start sagging away, then you unload from this point here, if you can see where I'm pointing, and you've got from there a similar sort of thing to here. And then, just to show you that it's quite doable, we've offered this within our software for a number of years, but very few people use it, is to control off the cod gauge itself. And here we actually get a much nicer control of the system. We load up, and then we turn around, go straight back down, and it's open to debate, but it seems like that separation there is a bit narrow. But it's a very neat control. And you can see then if we deliberately introduce a relaxation there, we're still holding at the same COD. How am I doing for the time?
It's okay. I've got 3 minutes.
Okay, perfect. So hopefully this will advance the slide at the moment. It says. Okay, so this is what if I plot that out against time, so that you can now separate red for the actuator displacement, blue for the cod gauge, green down here for your load. What you can see is pretty much what you'd expect with immediate unload, yielding, a yielding-like behaviour, and then straight back down. Then once we see the deliberate lag, the deliberate relaxation, you can see how the load is dropping off here. It's tailing back down. And you see a similar thing over here with the deliberate relaxation. And you see how we're forcing, how we've got a very slopey shouldered blue line while we're controlling in position, and when we control in the cod gauge itself, we're forcing the actuator to conform and do some interesting tricks to keep up. So, demonstration of what's possible. So what are the implications for measurement? Very briefly, once we've loaded for propagating state, there must continue to be either crack extension or plastic deformation or force relaxation in some way until you drop below an arrest point, for want of a better description. So that means for every unloading sequence, we are measuring some average between propagation and arrest, which is food for thought, I feel. But what I'm saying to you, whatever you do, is it's important to capture all the data and not miss any out, like the example I showed you. It's all important to use it consistently above all else. So what can we do to try and make a more robust approach? Flexibility is great for when you're doing research, but when we're trying to do a qualification of materials, that's not good because you're not going to get good interlab comparability. So the options that are there, straightforward thing, first off, control of the crack mouth opening rather than the actuator, the load line displacement, if you will. Reverse quickly. Also, not too bad, it's easy if you're using a hydraulic machine, but not everyone uses that. And the other one, which is a bit more tricky, is require a relaxation time before unload. Now, control-wise, it's fine, and it should always result in conservative values, as far as I can interpret it. But it requires some qualification. It requires some acceptance from the industry and from the standards bodies. So, just briefly wrapping up then, what we're seeing is more and more people asking us for industrial use of JIC testing systems, and unloading compliance is really the most popular route. Beware your test control, it does influence your results. Not everyone thinks about this, and more on your side than ours. Take care with your data handling and curve fitting. always consider what a good test looks like. This is what I say to people about all sorts of testing. I've probably used up my time, so questions at the end, I imagine.
No, we have
Oh, right,
time for
splendid. One or two now.
Yeah.
Thank you very much.